Welcome to EDU World Space.
So a couple things to keep in mind when looking at orbits of highly eccentric objects like Halley's. So we recall that A is the length of the semimajor axis. And this is what you get by using Kepler's third law. So the length of the longer axis along the ellipse. There is a focus, so if you use the equation R equals A times 1 minus eccentricity squared over 1 plus eccentricity cosine theta, then this is centered at the primary focus. Which means the sun. Okay. I have shifted the orbit so that it is centered, and then you can readily see the semiminor axis, the B, that shows up in the standard form of the elliptical equation. And where is the focus? So the focus is actually very close to what's called the perihelion location, which means near the sun. So it's the point on the orbit nearest the sun, whereas aphelion is way, way far away. Ap meaning far away, para meaning close, and of course helion meaning the sun. And what's true about an ellipse, so this is a geometric thing, is that the distance between the center marking and the focus is A times epsilon. The other thing that is kind of interesting to be aware of is that the sun, the focus, is A away from the point on the semiminor axis. So there's kind of a symmetry going on with the two foci. There's another focus on the other side that there's nothing there, but in real space. So the first thing that you can do with an orbit is, if you have some information, such as the period, you can use Kepler's third law. And that relates p squared directly to a cubed. If the period is in years, the a will be in astronomical units. So we know that it's 76 years for the p, and we want to take the cube root of that to get a, and that will give us a in astronomical units. And a, therefore, we can find is 17.942. And that tells us a lot about this orbit, that plus the eccentricity. So comets have very highly eccentric orbits. Eccentricities close to zero are circles, and as you approach 1, you get practically a straight line. So we're not quite straight line yet, but getting there. We can convert A into real meters, as we'll see. That might be a good thing to do. We can take the A, or any distance really, and convert by knowing the distance in 1 astronomical unit. I will use 1.496 times 10 to the 11th meters in 1 astronomical unit. So this could become helpful, as we'll see shortly, when we need to get velocities. So one of the things that we can do with Kepler's third law is recast the third law in Newton's form. So Newton is credited for figuring out that there is a constant that relates to the mass of our sun in terms of the third law. And this is where, if we put everything in SI units, we can actually calculate the mass of the sun. So we'll have to take the period as 76 years and convert that into seconds. Yeah, why not? And we can then put A in there, G. We can look that up in SI units. So newtons and meters and kilograms. And we can put that all together and solve for the mass of the sun. It's kind of a lot of digits, but it can certainly be done with a calculator. And we find that the mass of the sun is close to 2 times 10 to the 30th kilograms. I'll keep a few more sig figs just for good measure. Some other things we can do is start to look at the velocities of the comet in its 2 different positions. So kind of using the eccentricity and knowing that A is the semimajor axis, we can actually calculate both the aphelion and the perihelion distances. The perihelion is shorter than the semimajor axis by using the eccentricity. And we get a little bit over a half an astronomical unit. And we can convert that into real meters if we want. We'll go ahead and do that. And we can do a similar thing with the aphelion distance. Again, it gets a little further away by the eccentricity. And we could show with the geometry of the ellipse how that looks and verify this equation. But notice that the aphelion distance is almost 2 times the semi-major axis, almost the full length of that major axis away. And again, we can put this in meters. And I'm keeping the sig figs because I am going to need to work with velocities. So let's find the speeds at both the perihelion and the aphelion. And that takes a little bit of work, but there is a relationship derived in the chapter. It's equation number 2.33 in Osley and Carroll. And you can almost see that there's some energy relationships coming into play. So it looks almost like a absolute value of a potential energy with some eccentricities showing up. Okay, and working that out, I'll just show all the numbers. It's not too exciting, but we'll go ahead and show those. And I'll use the mass of the sun that I estimated in terms of kilograms. So this is where using the SI units is really going to become necessary, because you've got G in SI units, and you want the velocity to be in meters per second or kilometers per second to simplify it. And then you've got the eccentricity coming into play. And working all that out, I'm getting 54,560 meters per second. That is pretty serious. Not to fear, Halley's is bound to the sun. The aphelion velocity can then be found using conservation of angular momentum. You can always use conservation of angular momentum or energy to find velocity given a position or a distance from the sun. It may not always be an easy thing to do. The aphelion and perihelion points are easy because of the following. At those 2 points, the velocity is perpendicular to the radius at those 2 points, and those 2 points only. So basically, we don't need any angle. So reminder that angular momentum is mass and then r cross v. And typically, if your r and your v are not perpendicular, which they aren't for most parts of the orbit, you need a sine factor in there, a sine of the angle in between them, to extract the angular momentum magnitude. Here, we know that the r and the v are perpendicular at both of those points. So we can actually use the velocity we just found for the perihelion and the radius at perihelion related to the same at aphelion, and we can work that out. And I can even put my aphelion and perihelion distances in terms of astronomical units, because the units will cancel. And that's a really helpful thing. Yeah, and the units of meters per second will stick around. Okay, and so we find that the aphelion speed is very small compared to the perihelion speed. And we can even use that to compare the kinetic energy at aphelion to the kinetic energy at perihelion. Just take the square of the 2 speeds, and that ratio will tell you a lot. And actually, I think I want the obverse. I like big numbers, so let's turn this around. I have a better feeling for large numbers rather than very small digits. And yeah, we find that the kinetic energy at perihelion is thousands of times more than it is at aphelion. And of course, that kinetic energy came from converting gravitational potential energy way far away to the kinetic energy close up. Now there's one last speed that they are interested in finding, and I'll call that VB. And that is the velocity or the speed, I should say, when the comet crosses the semiminor axis. So I'll choose the point up at the top. And again, I could use conservation of angular momentum, but notice that our R, which points from the comet to the sun, for example, or from the sun to the comet, however you'd like it to point. I think I like it from the sun to the comet. Notice that that is not perpendicular to the tangent to the curve. There is an angle between those. And that angle is identical to the angle of the orbit itself. Plus or minus. Okay, so maybe they're adding up to 180 degrees. And how we can use the angular momentum. Let's just see how angular momentum conservation works. You could use either angular momentum or energy conservation. I am going to use angular momentum conservation with RB times VB times sine of theta, sorry. Cross products always involve the sine of theta. So that has got to equal either the R at perihelion, velocity at perihelion, or the same product for the aphelion. And so we'd be okay. We know that RB is the same as the semimajor axis. We're looking for VB. Let's see if we can find the angle. We can go back to the orbit equation. And we'll find something quite useful with this equation, which is why this is kind of fun. So at point B, crossing the semiminor axis, the R is actually equal to A. And we can cancel it out of the orbit equation and cross multiply. One will cancel, and a factor of epsilon will cancel. And so we see that the solution to this is cosine of theta is minus epsilon. Okay, so that's kind of an interesting thing, that as the particle crosses the semi-minor axis, the cosine of the angle is minus epsilon. And solving for this, or the eccentricity, I should say, working this out, we find that theta is angle whose cosine is minus 0.9673. Yeah, let's get that in right. Which is about 165.3 degrees. So we can now use conservation of energy, that A which is 17.942 times the velocity times sine of 165.3 degrees. And we can use either the perihelion distance or the aphelion. We'll use the perihelion. And the perihelion velocity, which is a really high number. And dividing all that out, of course, we're looking for the VB, so we have to divide everything out. We find that it's somewhere intermediate between the very slow and the very fast. No surprise there. We'll approximate it as 7,030 meters per second.